Hi everyone, we're solving this physics paper today. This is 9702, paper 42, May June 2023. It's 9702, paper 42, May June 2023, physics paper 4. Alright, so before we begin, let's take a look at the threshold. Also, I have great news. The channel just hit 10,000 subs, so thank you for all the love and support. So if you do like the content, please drop a like, uh, hit the subscribe button, and look forward to more content. I'm releasing physics paper 4 after a long time. I plan to release physics paper 5 and chemistry paper 4 next week. I plan to release all the papers before your October-November session, alright? And if you need more help with, one-to-one sessions, then solved question papers from 2000, 2 to 2023, as well as my notes for physics and chemistry, please do consider supporting me on Patreon. It's patreon.com/CAI paper solved. So there are 3 tiers. One is just for support. There's another tier for ad-free videos and access to chapter-wise notes for physics and chem, and solved question papers for physics, chemistry, bio, paper 1, paper 2, paper 4, and paper 5, as well as math P1, P3, M1, and S1 from 2002 to 2023 onwards. Also, for the ultimate learning experience, you actually get access to video chats with me once or twice a month, and also access to some private videos. I'm working on those currently for physics, chemistry, math, and bio. Priority for question paper solving requests, and your name in the credits on screen on all of my YouTube videos. Alright, so let's take a look at the threshold. So this is paper 4.2. So the maximum raw mark is 100. A is at 63. B is at 51. C is at 41. D is at 31. And E is at 20. So yeah, it was on average just like usual. The mark distribution looks fine. So let's write that down. The maximum raw mark is 100. A was at 63. B was at 51. C was at 41. D was at 31. And E was at 20. So A star should be at around, look at the gap, it's about 10 to 11 marks. Here it's 12. So it might be, 10 or 11 marks or 12 marks above this. So 11 marks above this is actually 74. So you needed a 74 or 75 to get an A star in this paper. So yeah, let's not waste any time, and let's begin. I'm solving paper 4.2 for today, but I'm gonna be releasing paper 4.1 or 4.3, whatever you want to call it, soon, by next month. All right, let's begin. So this is the data sheet that you have access to. So let's begin. State Newton's law of gravitation. So according to Newton's law of gravitation, what do we know? That the gravitational force is directly proportional to the product of the masses. And you also need to mention one more thing which they did not mention here, which is optional. So you could say that the gravitational force between point masses. Okay, so let's just edit that. Wait. Let me just edit this over here. The gravitational force between 2 point masses this was a compulsory point before, but now it has become optional, the point masses part. The gravitational force between 2 point masses is directly proportional to the product of the masses and inversely proportional to the square of their separation. We're talking about the force, right? And inversely proportional to the square of their separation. Okay, so the gravitational force between 2 point masses is directly proportional to the product of the masses and inversely proportional to the square of their separation, where r is the separation. A satellite is in a circular orbit around the planet. The radius of the orbit is r and the period of the orbit is t. The planet is a uniform sphere. Use Newton's law of gravitation to show that r and t are related by this equation. Okay, so we know that the gravitational force, which is gmm by r square, this is basically a planet, and we have a satellite somewhere over here. Now, basically, it is in an orbit, and the radius of the orbit is r, which is also the separation, the distance between the centers. So the gravitational force actually provides the centripetal force. So whenever you see time, okay, you will opt for m omega square r rather than mv square by r. So I'm going to go for m omega square r, where m is the smaller mass. Okay, it's the centripetal force felt by the satellite. So the gravitational force between the two planets provides the centripetal force of the satellite. Now we can get rid of the m's, and we end up with gm is equal to omega square r cube. Now omega can be written as 2 pi by t. We know that omega equals to 2 pi by t. So we actually end up with gm is equal to 4 pi square by t square into r cube, and finally gmt square is equal to 4 pi square r cube, shown. Let's move on to the next part. The Earth may be considered to be a uniform sphere of mass 5.98 into 10 power 24 kg. So the data is given to 3 significant figures, and we also have another point. We have the radius of the Earth as 6.37 into 10 power 6 meters. A geostationary satellite is in orbit around the Earth. Use the expression in B to determine the height of the satellite above the Earth's surface. Interesting. So since it's a geostationary satellite, it has a time period equal to that of the Earth, the period of rotation of the Earth, right? Which is 24 hours for 1 day, and it will revolve around the Earth the same way. So the period of rotation is the same, or revolution for the satellite, and rotation for the Earth. We know that the Earth is revolving around the sun, but it is also rotating. It completes one rotation in 24 hours, and the satellite is following it in the same direction, which is, as you guys know, west to east, right? That's the direction. Now, use the expression in B to determine the height of the satellite above the Earth's surface. So let's do this. Now, we know that g is the universal gravitational constant. We have the value of m. We know the value of t, it's 24 hours. And it's just that r is composed of two things. You guys need to know this. R is composed of two things. R is their separation, right? But it has two components. One is the radius of the orbit, which is this part over here, and the other is the radius of the Earth. Now we need to find out the height. So the radius, sorry, my bad. The r that we have over here, capital R, is the radius of the orbit. Okay, that is r. This one over here is the height of the satellite above the Earth's surface, and this one over here is the radius of the Earth itself. So can we write this, that the radius of the orbit equals to the radius of the planet plus the height of the planet, basically? Height of the satellite above the planet. So let's use that information to solve this. We know that GMT square is equal to 4 pi square r cube. Now, we also know that G is 6.67 into 10 to the power minus 11 times the mass is 5.98 into 10 to the power 24, and the time is 24 hours, which is 24 into 3600 or 16 to 60. I converted it into seconds. Whole square equals to 4 pi square into r cube. So let's solve this. 6.67 into 10 to the power minus 11 times 5.98 into 10 to the power 24 times 24 into 3600 whole square divided by 4 pi square. So we get a value of r cube equals to 7.54 times 10 to the power 22, and cubic root answer gives me this value. R is equal to 1, 2, 3, 4, 5, 6, 7, 4.22 in 10 power 7. I noticed that the data is given to 3SF, so I'm opting for a 3SF answer. Now I give you the formula that the radius of the orbit is equal to r plus h. So radius of the orbit is equal to r plus h. So height is equal to 4.22 into 10 to the power 7 meters minus 6.37 into 10 power 6 meters, the radius of the Earth, minus 6.37 into 10 to the power 6, which gives me an answer of height equals to 3.59, 1, 2, 3, 4, 5, 6, 7 into 10 to the power 7 meters. Okay, 3.59 into 10 to the power 7 meters. Now, at the end, we need to, consider our data. All the raw data that was given had 3 significant figures, right? Now, we did use 24 hours though, which is given to 2SF. So according to that, in the mark scheme, they actually opted for a, wait, let me write this down, h equals to r minus r. So in the mark scheme, they actually opted for a 2 significant figure answer, 3.6 times 10 to the power 7. But it would be fine if you gave a 3SF answer as well. But remember that most of the time, 2 significant figures is the way to go. It's the safer bet, alright? Let's move on to the next one. Another satellite is in a circular orbit around the Earth with the same orbital radius and period as the satellite in C. Calculate the angular speed of the satellite in its orbit. Give a unit with your answer. So the angular speed or angular velocity, what is the formula for that? Omega is equal to 2 pi by t. So 2 pi by t, the time is the same, which is 24 hours. So that's 24 times 60 times 60. So 2 pi by 24 into 60 into 60 is 7.3. Our data is given to 2SF minimum, so 7.3. It was 7.27, which is 7.3 into 10 to the power minus 5, and it is rad per second, radians per second. Okay, fine. Despite having the same orbital period, the orbit of this satellite is not geostationary. Suggest 2 ways in which the orbit of this satellite could be different from the orbit of the satellite in C. So what do we know? Geostationary satellites have period of 24 hours compared to the Earth. It rotates from west to east, and it has an equatorial orbit. It rotates, or it has a revolution above the equator. So since it is not geostationary, suggest 2 ways in which this satellite, this satellite differs from our geostationary one. So we have to say the things in the opposite way. We have to say that the orbit is not from west to east, or we could say the orbit is from east to west. Fine. And the orbit is not equatorial, or the orbit is polar. Okay. Orbit is not equatorial, or we could say that the orbit is polar. Fine. So that is how this satellite differs from our previous one. Moving on to question number 2. I actually had this question already done before, So let's talk about it. It's fine. State what is meant by an ideal gas. From 2022 onwards, the definition changed by a bit. It is a gas that obeys the law PV is proportional to T for all values of pressure, volume, and temperature, where T is the thermodynamic temperature or the temperature in Kelvin. You specifically need to state these, okay, or else you won't get marks. You need to say that you need to refer to T. Now state the temperature in degrees Celsius of absolute zero. We know that the actual value is minus 273.15 degrees Celsius. That's the important part, okay? Beforehand in O levels, maybe you knew it as 273 minus 273, but more precisely to two decimal places, it is minus 273.15. Okay. Now, moving on to the next part, a sealed vessel contains a mass of 0.0424 kg of an ideal gas at 227 degrees Celsius. The pressure of the gas is 1.37 into 10 power 5 pascals, and the volume of the gas is 0.640 meter cube. Calculate the number of molecules of the gas in the vessel. So its PV is equal to NKT. We know that there are three major formulas: PV equals to nRT, PV equals to NKT, PV equals to 1 by 3 NMC square. So typically, whenever they want the number of molecules, you're going to go for PV equals to NKT. It's the easiest approach. So pressure is in pascals, volume is in meter cube, so that's fine. We can find out n. K is the Boltzmann constant. The data is given in the data sheet. It's 1.38 into 10 to the power minus 23, as you can see here. It's 1.38 into 10 power minus 23. That's K. So that's that. Yeah. And T is the temperature in Kelvin, so you got to convert 227 degrees Celsius to Kelvin by adding 273. So hear me out. Here you don't have to add 273.15. When they want a specific temperature, when they ask for a specific temperature in a blank or something, only then do you take that into consideration. So let's do the math. It's pretty straightforward. You did this in AS chemistry. After solving it, you're going to get this value of N is equal to 1.27 times 10 to the power 25 after you do it in your calculator. Okay, so 1 mark for the formula, 1 mark for the working, 1 mark for the answer. So yeah, this was probably in the last answer, maybe because we used 24, which was given to two significant figures. That's why our final answer was 2SF. But here, as you can see, all the data is given to three significant figures, all of it including K. That is exactly why we give our final answer to three significant figures as well. Okay, see if that's fine. Let's move on to the next one. The mass of one molecule of the gas. So basically we know that the mass of the whole gas is 0.0424 kg. So we know the number of molecules now. So I'm going to teach you another formula. Check this out. So you can write that Nm is equal to the total mass of the gas. Nm is equal to total mass. So I use this formula here actually. Nm equals to total mass. So the mass of one molecule, where N is the number of particles and M is the mass of one molecule. Okay, so using that we can find this out. So mass of one molecule equals to total mass divided by number of particles, 1.27 into 10 to the power 25. So let's do that. 0.0424 divided by 1.27, 10 to the power 25. So that is 3.34 into 10 power minus 27 to three significant figures, since I've used 3SF till now. Finally, the root mean square speed of the molecules of the gas. For this, we can use two formulas. We can either go for PV equals to 1 by 3 NMC square, or we can go for KE is equal to 3 by 2 KT. It's up to you guys. Okay, so I showed both methods here. See if you guys get it. So one of them is this: kinetic energy is equal to 3 by 2 kT. For an ideal gas, we know that Ke is equal to 3 by 2 kT, and kinetic energy is half mc square, where c square is mean square speed. So it's half into mass of one molecule, 3.34 into 10 to the power minus 27. So let's do that. 3.34 into 10 power minus 27 times 0.5 is equal to 3 by 2 kT. Now the temperature of the gas is, we know it has to be in Kelvin. 227 plus 273 is actually 500. We know that. So let's do that. All right. So we end up with half mc square is equal to 3 by 2 kT. So it's 3 by 2 into Boltzmann constant, 1.3 in 10 power minus 23 into 500, divided by the answer on the left hand side, which gives you 6.20 into 10 power 10 power 6. And after you root over answer, you get a value of 2489, which is rounded off to 2490 meters per second. Okay, so that is one root. The other root being PV equals to 1 by 3 nmc square, where P and V are the pressure and volume respectively. We have those over here, is equal to 1 by 3 into, remember that I taught you Nm is the mass of the gas, right? Nm is the total mass of the gas, which is 0.0424, 0.0424 times c square. So you get the same value as well on that side. Okay, so see if you guys get it. If you have any queries, please feel free to comment below. Otherwise, we can move on. Now, let's move on to the next one. Now, this was a rather complicated graph, honestly. The gas in B is now cooled gradually to absolute zero. On figure 2.1, sketch the variation with thermodynamic temperature of the RMS speed of the molecule. So to get this, we need to do some math. Come on, let me teach you. This can take some time to make you guys understand. Just give me a bit though. Way up. I need to erase these. Man, I drew so many diagrams. My students weren't getting it, sadly. Anyway, so hear me out. We need to know the basics first, okay? So check this out. Y is equal to x. What does this graph look like? Straight line passing to the origin. Good. Y is equal to x squared. Now, what does this look like? Y against x. It's going to look like this. But what if I had x is like this, y against x squared? Then this same graph would be a straight line passing to the origin. So it depends on what axis you have and what you're trying to draw, because we know the y is proportional to x squared. So if you draw it against x, it's going to be a curved line, but if you draw it against x squared, it's going to be a straight line. One other thing you guys need to know is, this is the same as, this is the same as root y is equal to x. It's the same thing. And then another one, y is equal to root x, or y square is equal to x. Let's check this out. Y is equal to root x, or y square is equal to x. So if you draw a graph of y square against x, it's going to look like this if the axes are y and x respectively. And check the other one. If you draw the same graph over here, however, the axes are y square against x, it's going to be a straight line passing to the origin like this. These are the basics that you guys need to get. Then we can move on to the variations that we have. Okay, ready? So I'm going to give you a basic example. Check this. What if we know that kinetic energy is equal to half mv square, right? So what if I draw a graph of this? Kinetic energy on the y-axis and v square on the x-axis. Then it's going to be a straight line passing to the origin. However, if I draw a graph like this, kinetic energy against v, it's going to be a curve like this. Similarly, like, y is equal to x, y is equal to x square, right? Because kinetic energy is y and x square is the v square, right? So if you draw against an axis of v square, it's going to be a straight line passing to origin. But if you draw against an axis of x or just v, it's going to be a curve, because v changes faster than k, right, due to the square. Now let's come to the question at hand. Okay, it's something related to RMS speed and the temperature. So we know that, wait up, which equation do we have to use here? Let me think. Thermodynamic temperature against R. Okay, fine. So we know that kinetic energy is equal to 3 by 2 kT. Fine. And kinetic energy can be written as half m c square is equal to 3 by 2 kT. So we know that this one over here and this one over here, these are constants. So we can ultimately write that c square is proportional to t. So now the x's might also be interchanged, right? So for example, it is temperature on the x-axis, fine. So check this out. If we had a graph of maybe, kinetic energy against temperature, it would be a straight line passing through the origin. Okay, if we had a graph of c square against temperature, it would also be a straight line passing through the origin. But now check this out. This is the last variation that you guys need to know. Wait, check this. What if we have a graph of, same variation, but same variation, it's c square is proportional to t, but RMS speed on the left hand side, which is root over of c against temperature. Now it's gonna be a bit different. So this graph is basically, you guys need to understand that this graph is essentially y square is equal to x, right? Because x does not have a power, does not have a square, but y on the other hand has a square. Just like, I taught you in that case, kinetic energy is equal to half mv square, or kinetic energy is proportional to v square. We can write this as y is equal to x square. Similarly, this is just inverted. It is c square is proportional to t, or y square is equal to x. And what did I teach you? If you had a scale of c square against t, it would be a straight line passing through the origin. But since we don't have c square over here, but rather root over of c square, which is RMSc, it's going to be a curve like this. Okay, so simply it's going to be the graph of y square is equal to x. This one over here. However, the axis isn't c square, the axis is CRMS, or just c, root over of the mean square speed. Okay, so it's the graph of y square against x on the axis of y against x. See if you guys get it. This was a rather complicated graph to score full marks in. You need to have a good concept. Also, as you can see that the velocity, we are talking about the velocity at 500 degrees Celsius, which is 2490, right? So at 500 degrees Celsius, it is, like this. There you go. And this velocity is, you don't need to mention that, but it's 2490. But you need to show that it is reaching this particular V, okay? This particular V at 500 Kelvin, all right? Not degrees Celsius, my bad. Let's move on to question number 3. A lot of explaining over there. So yeah, I have this one done as well. State the first law of thermodynamics. So we know that the increase in internal energy of a system is equal to the sum of the work done on the system and the thermal energy supplied to the system. Fine. So if you just write change, you'll only get 1 mark. So you particularly need to state that del U is the increase in internal energy of a system, and plus W is the work done on the system. These are the keywords. Okay, if you don't write this, you don't get field marks on the system. And Q is the thermal energy supplied to the system. They wrote this in a different way though. Let me show you what they wrote. Where W is equal to this and del Q is equal to the energy transferred to the system. Energy transferred to the system by heating. You could also word this as thermal energy supplied to the system. Same thing, okay? It doesn't really matter. See if you guys get it, okay? And you didn't need to mention the formula, I just did because they were talking about symbols. You could just write increase in internal energy of a system is equal to the work done on the system and energy transferred to the system by heating. Alright, let's move on to the next one. So next one is rather interesting. This is the diagram for an ideal gas. We know that internal energy is actually equal to the sum of kinetic energy and potential energy the random distribution of Ke and Pe of all the particles in a system. And we know that for an ideal gas there is no Pe, there is only Ke, and we know that the formula of K is equal to 3 by 2 Kt. So as you can see, you started from A, you went to B to C to D and came back to A again. So what is the net change in temperature? It is 0. You come back to your original temp. So in throughout the process you might be gaining internal energy, you might be losing internal energy, but at the end of the process the net internal energy change is 0. That's what you guys need to understand. That is a common question that they ask most of the time. Now so for changes like A to B, always remember that an increase in volume is associated with work done by the system. Think of a piston, right? Think of a piston. If the gas particles, push out against the atmosphere, what happens to the volume? The volume will increase. So an increase in volume is associated with work done by the system. It's negative. However, if you pushed down, right? What if you pushed down? What if you push down? Then the volume would decrease. So a decrease in volume is associated with an increase in work done or work done on the system. Okay, that's what you need to know. That a decrease in volume is actually work done on the system. So for example, from A to B, what's happening to the volume? Volume is actually decreasing. So work done over here is positive. And another thing you need to know is the work done by a gas is P del V. This is the formula for work done. So if there is no change in volume at constant pressure, then work done is 0. For example, B to C, there is a change in pressure but no change in volume. So what is the work done on or by the gas? It's 0. So in these two transitions, the work done is 0. And from C to D again, since the volume is increasing, so the work done is negative in that case. All right, so that's what they asked you over here. Let's fill this up. I'll explain again. So from A to B, as we know that the volume is decreasing, so the work done must be positive. Okay, we need to put a tick mark over here. Then from B to C, since the volume remains unchanged, the work done on the gas is 0. Okay. Then from A to B, let's check the change in internal energy. We know that the formula for internal energy is actually, del U is equal to del Q plus del W. Now nothing was stated about the thermal energy over here. Nothing was stated, right? Whether any heating was applied to the system or heat was lost. So we are just going to assume that it was 0 in all cases. And if W is in fact positive, right? If this W is positive over here, then del U must also be positive, assuming that Q is 0. So the internal energy of the system must increase. Logically, right? However, we cannot make assumptions. We cannot make assumptions all the time because there might be thermal energy, taken in or out. So let's just think about it carefully before jumping to conclusions. Let's just think about it carefully, okay? Because unless you see the word suddenly, you cannot jump to the conclusion that Q is in fact 0. Okay, you cannot jump to that conclusion. Because when you see the word suddenly, it usually indicates that no heat entered or left the system because it happened so fast. Like, we can take a look at the next question to actually figure out how to, fill up the table that we have. Let's try to figure this out. Use the first law of thermodynamics to describe and explain the energy transfers associated with one complete cycle ABCD. I just taught you guys. Like, if we come back to our original position, what happens to the internal energy? The net internal energy change is actually 0. The overall energy change, the overall internal energy change is 0. That's what you guys need to understand. That there is an overall internal energy change of 0. Del U over the whole cycle is 0. However, we need to figure a few things out over here. For example, let's compare each of the segments. From we started from A. So look at what happened at A. Compare AB. What happened over there? Work is done on the gas. And in CD, since the volume increased, work is done by the gas. But the pressure is the main factor. The pressure is the main factor. This is a really hard question to comprehend. Check this. At the level of AB, check this. What is the value of pressure? Maybe it's P1. And at the level of CD, what's the value of pressure? Maybe it's P2. You guys need to understand that P2 is in fact greater than P1. And I just taught you the formula of P del V over here, right? So the magnitudes, even though the change in volume is the same, check this, the change in volume, the decrease in volume or the increase in volume is the same for both cases, A to B and C to D. However, the value of W will be different because the value of W is P del V. So for the change A to B, the value of W is actually, since volume is decreasing, plus P1 del V. And for the change CD, W is actually negative since volume is increasing, so it's actually minus P2 del V. This is what you guys need to get. And you need to understand that the change in CD is greater than the change in AB, the work done. So in CD it was negative and in AB it was positive. So maybe, in CD it was, just for example, just hear me out. Maybe it was, minus 20 and in AB it was plus 15. So what's the net change in work done on or by the gas? It is minus 5. We know that W is 0 from B to C or D to A. Both cases W is actually 0. However, since the change CD, the same change in volume occurs at a higher pressure, that's why the work done by the gas during the change CD is actually greater in magnitude than the work done on the system or on the gas in the change AB. So there is a net loss of work done. So the net value of W is negative. But I just told you that, check this, I just told you that del U is equal to W plus Q. So since throughout the whole cycle, A, B, C, D, A again, del U is actually 0. If W is negative, then what must Q be to balance things out? Q must be positive to actually have a net value of 0 as well. This is the whole logic behind everything. So this was a very complex question. You need to have a high level of IQ to actually figure this out. So let's write this down now. So let's do this. We can either state that more work is done by gas in CD than is done on gas in AB. I could just write an extra point due to higher pressure during change CD. They should have mentioned that. And an alternate answer to this point was, you could say that, no work done on or by gas. Where? In BC and, what was it? BC and DA, I think. BC and DA. So, overall gas does work. So what does this second line mean? Since BC and DA had a value of 0, let's compare all of this. It's basically, and I'm going to assign values. Plus 15, 0, minus 20, 0. Check this. AB, BC, CD, DA. So plus 15, 0, minus 20, 0. So what is the net value? It's minus 5 joules, right? So overall, the gas does work. Work is done by the system overall. Okay, that's the first point that you guys need to write. It's a must. Okay, I honestly think that both points should have been written, but they are good with only one. Okay, so now we have to say that throughout the whole cycle, overall change in internal energy is 0. Fine. Now, finally, so therefore there must be and overall input of thermal energy. That is exactly what I was telling you guys. We cannot jump to the conclusion that there was no input or output of thermal energy because it wasn't mentioned in the question. If they said the word, it happens suddenly, or like there was no loss or gain of heat, we could assume that. But it's not an assumption, then it's a fact. But here we cannot assume things. So use the first law of thermodynamics, which is del U equals to del Q plus del W. We figured out that the whole change in internal energy was zero throughout the cycle. Overall del W was negative, so overall del Q must be positive. That is the logic behind this. Okay. See if you guys get it. I tried to break it down as simply as possible, but you guys need to understand that this was a really high level question. It is not for everyone. These 3 marks is if you want to get that country heist or world heist or even secure your A star, right? Honestly, you would there are easier questions to secure your A star. This was honestly on a higher level than that. So use the first law to describe and explain the energy transfers associated with one complete cycle. So we need to talk about 3 energy changes: the change in internal energy, change in thermal energy, and change in the work done on or by the system. We mentioned all 3. Now let's come back to this table and see if we figured it out. So I'm gonna teach you something, okay? It's basically common sense, but sometimes we tend to forget. Check this. What happens when you boil a liquid? The liquid changes to gas. What happens when you heat a gas? Suppose you have a gas in a piston and we applied heat. Now, what will happen to the gas molecules? They will move faster, they will try to expand, and they will push the piston against they will work against the atmosphere and push the piston. So, when you heat it, the gas expands. So what change have we just seen? When you input thermal energy, the gas expands, volume increases, and I just told you that if volume increases, work done will be negative. So remember that these two changes they always happen together. When you heat a gas, the volume increases when you heat a gas. That's what you need to remember. When you heat a gas, the volume tends to increase and work done is negative. Similarly, on the other side, what happened during change AB? During change AB, the thing is, the volume actually decreased, so work was done on it. So when could this happen? Check this. What if this was our initial volume and the volume decreased? So if you do not give any external pressure, that is still possible. How? If the gas is cooled or if it loses heat, if it gives out heat. So if Q is negative, there is a tendency for the gas to move with less speeds and contract actually. And at the same time, volume will decrease, so work done is actually positive. So since there was no mention of happening suddenly, or thermal energy was not lost or not given, so we cannot assume things, and we need to give the benefit of the doubt that whenever volume decreases, work is done on the system. Okay, and the change in Q will actually be negative. So for change AB, this is what's happening. We know that del U equals to Q plus W. So Q is actually negative since it cooled, the gas cooled, and W is positive. That's what we figured out initially. Okay, and for change B to C, let's check this out. What happened during B to C? We know that the work done on the gas is actually zero because there was no change in volume, but pressure increased. This is also really important. So hear me out. Basically, this can happen in one case. Suppose we keep volume constant. Suppose we keep volume constant. Suppose it's not moving. What is the origin of pressure of a gas? Basically, it originates due to the collision of the gaseous particles with the walls of the container. So if it collides more, we know that pressure is force by area. So if it collides with more force, the pressure generated will be higher. As you can see from change B to C, the pressure actually increased to a higher value. So they are colliding with more force. How is that possible? If the molecules move faster, that means they have higher kinetic energy, and we know that K is equal to 3 by 2 kT. So look at the backtracking. If V is constant and pressure increases, we know that this is, we have a law. We have Charles' law where pressure is constant, Boyle's law where temperature is constant. I forgot the name, but there's another law where volume is constant, and we say that P is proportional to T. Well, let me just Google the name. Law for pressure proportional to thermodynamic temp. Yeah, it's the law of Gay-Lussac. It's for constant volume, pressure is proportional to temp, because if you increase the temperature, kinetic energy increases, and the particles are moving at a faster rate. They're colliding with greater momentum with the walls of the container and generating greater pressure. This law isn't in your O level or A level syllabus. I think it should be included. Gay-Lussac, that's the law. So yeah, we can say that since, in this case, del U is equal to Q plus W. Clearly, we know for a fact that W is 0, right? W is 0. However, since volume was constant, since the pressure increased, it indicates that the temperature also increased. That means thermal energy must have been supplied to the system, which is why Q is positive. So if Q is positive and W is 0, what will be the value of U? It will also be positive. So this is an increase, that's for sure. So for change B to C, the change in internal energy is an increase, while the work done on the gas is 0. So that's what we figured out. And similarly, if you think about it in change D to A, right? In change D to A, since pressure decreased, so here the Q must have been negative, and here the Q is positive, and W is 0. Fine. Now, so parts BC and AD, they are balancing each other in a sense. We aren't sure about that either. But it's proportional, so it should balance. But if it did balance out, think about it. I just told you that the work done in sections CD and AB, they are not equal. Clearly, since this is minus 20 and maybe if this is plus 15, we somehow need to balance it. Okay, so let's check this out. How can this be possible? So I know for a fact that in part A to B, W is positive and Q is negative, because I taught you that if you do not put any external pressure, if a gas cools down, right? At constant pressure, if a gas cools down, work is done on the system and thermal energy is lost from the system. Similarly, in change C to D, since volume is increasing, that means it is expanding, it is doing work against the atmosphere. It is doing work against the atmosphere. And usually in this case, in these cases, the positive value of Q is much higher than the negative value of W. That's something that you need to know always. Okay. And in a case like this, okay, in a case like this, the internal energy change, it must be a decrease actually. Usually, when a gas cools down, Q always has the upper hand. Always remember this. W rarely has the upper hand. Q always has the upper hand in cases like this. In cases where volume is either increasing or volume is increasing. Increasing or decreasing, my bad. In fact, I want to show you an instance. Check this. Wait. I think it was in ON 2022 or May June 2022. Just let me check the question. We're wasting a lot of time here, but it's important that you guys understand this completely, or else we're gonna get stuck next time. Wait up. These are from papers that I've done. Okay, yeah, check this. Fine. So, yeah, as I was telling you guys, when a gas actually, the volume of a gas decreases, what change is associated? And why did this happen? Basically, because this is, if you're interested, this is from Magen 2022 variant 4.1. I've already solved that in a video. I'll put a link up top in a card. You can check that out if you haven't already. So when the volume of a gas decreases, what is possible? The gas may be cooled down, so W is positive, but Q is in fact negative. And I was telling you what exactly? Q usually takes the upper hand. So let's check that out. We need to check something from A to B. Check that from A to B, W should have a change of, it should be a positive change. As you can see, W is a positive change over here, and thermal energy is negative because it cooled down, and Q usually takes the upper hand. Important. And then let's go to the next one. This is just like our question at hand. From B to C, volume is constant, so work done is 0. But I just told you, according to Gay-Lussac's law, P is proportional to T. So, um, since the pressure increased to a higher value, P increased, so temperature must increase. So W is 0, but in this case, Q is positive because we need faster or more collisions. So in this case, this is 0, but in fact Q is positive. Okay, so that's the gist. And another thing I was talking about this point, if you ever see this word expands at constant temperature, that means the kinetic energy is constant. Okay, something like this. And you'll see words like cooled, but in this question it wasn't really mentioned. Okay, it wasn't really mentioned. And another thing, if cooling does occur at constant temperature, then the kinetic energy of the ideal gas is constant, and that means there is no change in internal energy. That is also one other thing that you need to keep in mind. Anyway, that is more or less the gist. I was telling you guys that basically whenever any change occurs at constant volume, okay, this is the cheat sheet. Let me give you the cheat sheet. Wait. So ultimately, if any changes or if any change occurs at constant volume, and this has to be a closed system, by the way, and it also has to be an ideal gas. Okay, closed system for the gas particles obviously, but heat can escape the system, so let's not write that for an ideal gas. So if the volume is constant by any chance, okay, that means P del V, so W will be 0. This is a fixed point. And if pressure increases, then temperature also increases, so Q must be positive. However, if pressure decreases, then T must also decrease, so Q will be negative. So that's phase 1. Next, we are going to see another change at constant pressure this time, but there is a change in volume. Okay, so the first one, if volume decreases, okay, if volume decreases, basically the work done will be positive and Q must be negative because the gas cooled down, which is why the gas cooled down. Oh, by the way, we can also write down, since W is 0 over here, in this case, for the first one, we can say that U is ultimately positive, and for the second one, U is negative. Now, as I was saying, when volume decreased due to cooling of the gas, Q is negative and W is positive, and we know that U is equal to Q plus W. But I told you that Q usually takes the upper hand, so in this case, U is usually negative. And on the other hand, if V increases due to heating of the gas, okay, so Q must be positive, but since volume increased, W must be negative. And I told you that Q always takes the upper hand in these cases, so we know that it's Q plus W. So since Q took the upper hand, U will be positive. So this is the ultimate cheat sheet, and I honestly didn't expect this from Cambridge. This question overall, starting from the table to the next point, is actually unreal, because it's so hard. You need to have really high IQ to solve this. Okay, so I took a lot of time explaining this. Hopefully you don't have any more confusions, and I hope this helps you in all your exams. Let's move on to question number 4. So let's do this. A small steel sphere is oscillating vertically on the end of a spring as shown. The velocity v of the sphere varies with displacement x from its equilibrium position according to this equation. Okay, where v is in centimeters per second and x is in centimeter. Calculate frequency of oscillation. So doesn't this formula look familiar? It's the formula for velocity. V is equal to plus minus omega root over x naught square minus x square. Fine. So if you match it with this, we can write v is equal to plus minus 9.7 root over 11.6 square minus x square. So what did you guys figure out? Omega is 9.7. So we can find out frequencies in this. We can write that omega equals to 9.7. And we can also write that omega equals to 2 pi f. So 2 pi f equals to 9.7 and f is equal to 9.7 by 2 pi. Let's do that. 9.7 by 2 pi is 1.54. But data is given to 2SF, so we should opt for a 2SF answer, which is 1.5 hertz. Fine. Show that the amplitude of the oscillation is 3.4. Sorry, I made a slight mistake over here. This 11.6, this thing, this is the whole squared value. Okay, it should be x naught square, but that squared value is actually 11.6 over here, alright? Because the square isn't present on top, right? Kind of like standard deviation variance. So we know that 11.6 is equal to x naught square. So x naught equals to root over 11.6. Let's find that out. Root over 11.6, which is 3.4 centimeters. That's awesome. Let's move on to the next one, maximum acceleration. We know that the formula for acceleration is in general a is equal to omega square x. So maximum acceleration should be a naught is equal to omega square x naught. We know that a is proportional to minus x, right? So let's do that. We know that omega is equal to 9.7. The unit is in meter per second squared though. So careful. So we need to convert. Do we? Okay, let's take it step by step. 9.7 square times x naught, which is 3.4. That gives us a value of a naught equals to 320.46. By the way, the unit that we got for this is in centimeter per second square. Now we need to convert it to meter by dividing it by 100. Or you could honestly do this in this step. We could take 9.7 is in radians per second, and this is in 3.4 into 10 power minus 2. So answer into 10 power minus 2 gives you an answer of 3.2 to 2 SF, right? 3.2 meter per second square. Fine. Next, sketch the variation of acceleration against x. So a naught is the maximum value. A naught is the maximum value that we have, remember, because a naught represents max axle. So let's try to do this. We know that because it's not a numerical scale on top, it's given in terms of a naught. We know that we get a naught when oscillations, the amplitude is 3.4. So let's find out 3.4 over here. This is 2, this is 4, this is 3, 3.2, 3.4, this one over here, and over here 3, 3.2, 3.4 over here. So, and it should be a straight line passing through the origin but with a negative gradient, right? So when x is negative at minus 3.4, a will in fact be positive. On the other hand, when x is positive at plus 3.4, we are going to have a negative maximum value of acceleration. So if I draw a straight line now, I think I should use a different color over here. Yeah. Just give me one sec. Honestly, that was fine. It's so hard to control it sometimes for OneNote. I usually use GoodNotes for taking notes for uni in my iPad. But, you know, I feel like OneNote is better for organizing question papers. But recently they released GoodNotes for Windows. I've been using that for my notes as well. So I might be shifting, you never know. So what do you guys use for doing question papers? I'm quite curious. Is it like hard copy or soft copy? Let me know in the comments below. I prefer going digitally. Like I've changed recently. Like for the last 2 years, everything is digital right now. Anyway, this should be the graph. It should be a straight line passing the origin with negative gradient, and the points are plus 3.4 minus a naught and minus 3.4 plus a naught. And yeah, that's it. That's it. If you want full marks, this is it. The ends should not exceed these 2 points, by the way. Should be plus 3.4 minus 3.4. Describe without calculation the interchange between potential energy and the kinetic energy of the oscillations. We know that for any pendulum, kinetic energy is maximum at the equilibrium position. And it is 0 at the end because it comes to rest momentarily. And yeah, GP is maximum at the ends, or potential energy is maximum at the ends. But the sum is always constant, right? So let's mention that. The sum of potential energy and kinetic energy is constant. Fine. Now we need to mention that at maximum displacement, where momentarily it comes to rest, at maximum displacement, you could either say that kinetic energy is 0 or potential energy is maximum. Fine. And also at 0 displacement, they are referring to equilibrium position. At 0 displacement, kinetic energy is maximum, or potential energy is minimum. Fine. See if you guys get it, and let me know if you have any queries. Moving on to question 5, it's a two-way switch. How many questions do we have in total? It's quite long. I guess 12 questions maybe. Oh, we just have 10, so that's pretty short. We're gonna be done soon, hopefully in like 1 hour. Two capacitors A and B are connected into the circuit shown in figure 5.1. Capacitor A has capacitance C and capacitor B has capacitance 3C. The electromotive force of the cell is V. The two-way switch is initially at position X, and capacitor B is initially uncharged. Okay, so B has a dead end, so it is not conducting electricity. State in terms of V and C expressions for the initial charge QA on the plate of capacitor A. Let's do this. So we know that for a capacitor, C is equal to Q by V. So Q is equal to CV. So initially plate A, capacitor A is being charged up. So the charge on each plate of the capacitor will be Q is equal to, let's do this. Q is equal to C times V. So QA is equal to CV essentially, right? So that's it. Next, the initial energy stored in capacitor. The formula for energy, there are three formulas. E is equal to half QV, half CV square, and half Q square by C. Because we know that V is equal to Q by C. If you input V is equal to Q by C over here, you're going to get half Q square by C. So we are always going to prefer this one, and they've mentioned that in terms of V and C. So we're going to go for EA is equal to half CV square. So that is half CV square. Fine. The two-way switch is now moved to position Y. Interesting. So we now move the switch to position Y over here. This is X. Okay. Now it's moved to position Y. Let me erase it properly. There you go. Okay. So what's gonna happen now? This is a dead end over here, so electricity won't conduct there. However, capacitor A will discharge. capacitor A will discharge through B, and finally charge, it will discharge, and on the other hand B will charge up. So if it was any other random component like a resistor, okay, what if this was just a resistor, then the capacitor A would completely discharge. Okay, this is really important. But now we're going to learn an interesting topic. It's called charge sharing. The charge will be shared between the two capacitors. So let's do this. The two-way switch is now moved to position Y. State and explain what happens to a charge that was initially on the plates of capacitor A. So the important thing that you need to understand is that not all of it goes to B. So basically, if it was a resistor or any other component, just hear me out, all of it would be lost. But since it's another capacitor which is capable of charging as well, some of it will transfer to B. Now, how much of it will transfer? We'll figure that out. It actually depends on your capacitance, okay? So we have to say that some, okay? Some of the charge transfers to the plates of capacitor B. I have never seen a charge sharing question. First time. I usually teach this. These are in my notes. But if you want those notes, please consider supporting me on Patreon. On the second tier, you get access to the notes, and on the third tier, you get access to video calls along with the notes and my solved question papers for all the past years. So for charge sharing, if it's going to another capacitor, some of it will be transferred to the plate of capacitor B. Now, if they had equal capacitance, what would happen? Both of them would share equally. Now we stated what happens, and let's explain what happens now. So the explanation is, charge will only flow, okay, whenever there is a potential difference. When there is no potential difference anymore, charge flow will stop. For example, in the initial scenario, when we had the battery like this with capacitor A, when we had an initial scenario like this with capacitor A, this had a voltage of 9 volts, for example, and this had a voltage of 9 as well. So charge kept on flowing until, charge kept on flowing until it was saturated and it got a voltage of 9 as well. So charge keeps on flowing until there is no potential difference anymore, or we could say that until voltage has become equal for both components. Okay, so suppose this had 9 volts and suppose this had 0. So this will keep on decreasing. Maybe it's gonna reach something like 4.5 volts maybe, and this is also going to reach 4.5 if they had identical capacitance, by the way, but they don't. Okay, so the values, it won't be at the midpoint. It won't be 4.5, this won't be 4.5, maybe it will be a bit more. Since capacitor A has capacitance A, I'll get to this point soon. This is really important. I haven't seen a question like this, by the way, before. This is a really important topic. But yeah, the flow will only happen till potential difference is obliterated. So we can state that the explanation is, transfer is because the potential difference across the capacitors are not equal, right? Or we could state that transfer stops when the potential differences, when the PDs across the capacitors become equal. This is damn important, guys. Please do go through this. This is on another level. This variant was in general hard. I get why my students were complaining after the exam. Okay, let's move on to the next part. Show that the final potential difference VB across capacitor B is given by this expression. This is really important. Okay, so guys, we need to know something important. um, capacitor A has capacitance C, while capacitor B has capacitance 3C. This is extremely important, okay? So suppose we know that the initial EMF of the battery was V. It's mentioned over here, it's V. So clearly V is going to decrease between the two capacitors. It has to be shared, right? There is going to be charge sharing. So this something important that you need to know about charge sharing is that charge cannot be destroyed. It can't be created either. So the initial charge that you had on each plate of capacitor A, which was CV, this is going to be shared between the two capacitors. A will decrease the charge and B will gain some charge. And the value of V of both the capacitors must be the same. So charge flow will continue as long as PD is not stabilized between them, okay? So A has a capacitance of it has a capacitance of C, while B has a capacitance of 3C. Fine. So let's begin. Now I wanted to say something. If this had an initial value of 9 volts and this was 0, it could be 4.5 volts and this could increase to 4.5. When was this possible? If both of them had identical capacitance. But since this has higher capacitance than C, it will be a lower value, okay? So let's do this. So what is the basis of doing this? Let's try to figure it out. Charge flow will continue until VA is equal to VB, okay? Charge will flow, you can mention that. Charge will flow until VA becomes equal to VB. Fine. Next, charge will be shared between them. What does that mean? QA, that means charge on plate of A plus charge on plate of B will be equal to the net charge, which is CV, the initial charge, CV. Okay, it will be equal to the... So we can't write QA over here because it will be misleading, because this QA was CV. But now we are mentioning the new charge on each plate of A. Okay. So let's do this now. We know that the formula for C is equal to Q by V and Q is equal to CV. So we can actually write the new charge, right? The new charge on A is actually equal to hear me out. For A, what was the capacitance? The capacitance was C, right? So C times VA plus what is the capacitance of B? It is 3C. 3C times VB is equal to CV. This is what we end up with. Now we want to find out VB. So what am I going to substitute? I'm going to substitute this one. I'm going to write VA in terms of VB, which is C times VB plus 3C VB is equal to CV. We can actually get rid of C on its side, right? This can be written as, wait, let me move it to this side. We can write 4C VB is equal to CV. We can get rid of C on its side, so VB is ultimately equal to V by 4. That is shown, okay? So if you ever get a charge sharing sum, this is how you do it. I'm going to give a quick overview of charge sharing. When to understand is charge sharing? Initially, a capacitor will be connected across the battery and it will be charged. Then it will be allowed to discharge through another capacitor. So what will be maintained? Why does the charge flow happen and how long will it occur? Charge flow occurs because there is a potential difference between the two capacitors, and it will continue to occur until voltage is stabilized or becomes equal between them. And two things that must be remembered are the voltage at the end will be equal for both capacitors, and the initial charge on each plate of the first capacitor will be shared among them. So that at the end the total charge will be equal to the initial charge, okay, and the voltage will be the same. That is what you guys need to remember, and the value will decrease below the initial EMF, okay, it must be lower. Now determine an expression in terms of VNC for the decrease in the total energy that is stored in the capacitors as a result of the change of the position of the switch. Okay, By the way, guys, there was another route in the mark scheme. I'll show you that route as well to do this one. So that route is the total capacitance now is 4C, because this capacitor has 3C while the other has C. They are connected in parallel, actually, overall, the total capacitance. Like now they may look like series, but compared to the battery, they are connected in parallel. But this doesn't really make a lot of sense, honestly, because they are connected in series. Charge sharing actually occurs in series. But they've used the fact that, what is constant in a parallel circuit? Voltage is constant in a parallel circuit. So they are basically acting like two batteries that are in parallel, right? Check this. What happens when you connect two batteries like this? Basically, if this is 2 and this is also 2, right? Does that make sense? It basically acts as a parallel setup, right? 2 volts each. So yeah, it's like a parallel set of batteries. So voltage is conserved if there are like two resistors over here. So here the batteries can have different values, they can have different values, the two cells or batteries. But yeah, in this setup, ultimately we're going to get two cells or two capacitors that have equal voltage. So it is acting like a parallel circuit, honestly speaking. So I take it back when I said that we need to consider it in series. We actually think of it as a parallel setup during charge sharing, because remember, voltage is same for both of them, but charge is different. Just like voltage same, current different, it's voltage same, charge different. Okay, so the total capacitance is 4C for a parallel setup. This is A, this is B, 3C, and this is C. And yeah, we know that the charge, total charge, is, the formula is CV, the initial charge that we had. Now the formula for voltage is Q by C. So if you want to find out VB for this guy over here, the total charge is CV, and the capacitance is, the total capacitance, right, is in fact 4C. So if you do get rid of that, we are gonna get VB is equal to V by 4. Okay, so this is just a quick way of doing it. It's important that but it's kind of like potential divider, the whole thing. Like you can actually do it in terms of the ratio of their capacitance. That was what I was telling you, that how much voltage one gets, sorry, how much charge one gets is actually dependent on the capacitance. Like we learned in AS physics that in potential divider, how much voltage one gets depends on the resistance, right? And here, since voltage is constant, how much charge one gets is dependent on the capacitance itself. Okay, this is really important. And yeah, so this is another formula that I can teach you. You guys know that C is equal to Q by V, right? And we know that V is the same for them. V is equal to Q by C. So since both of them have the same voltage, can we write this? Since they have this different charge. For A, okay? For A it is QA by CA. And for B it is QB by CB. Right? And we also know the values of C. Like for A, the capacitance was C. And for B, the capacitance was 3C. So if you get rid of these, I told you that charge is based on capacitance. So QB actually has 3 times the charge of QA. This is how you can find out that, like, this question can come in the future. How much charge was stored on each plate of capacitor B? It will be now 3 times that of capacitor A. And if you're asked to find out the charge anyway, you know that it's Q is equal to CV. You have the value of voltage for both of them is V by 4, and you just need to multiply it by the capacitance. So for A it will be CV by 4, and for B it will be 3CV by 4. That is the basic thing I wanted to teach you, okay? So hopefully charge sharing has been clarified now, and you can face any question in the future. Okay, determine an expression in terms of VNC for the decrease in total energy. Okay, so let's find out the energy now, the total final energy. Total final energy. So that is half CV square, but now we have to use the new capacitance. What did I just teach you? That the total capacitance of the setup, since it's a parallel setup, it is actually 4C. So half into 4C, and what is the new voltage of the setup? It is actually V by 4, right? Half CV square, so that is V by 4 square. So 2C into V square by 16, which is 1 by 8 CV square. Now, what is the change in total energy stored? The initial energy was half CV square, minus 1 by 8 CV square. So let's do that. 1 by 2 minus 1 by 8 gives a value of 3 by 8. 3 by 8 CV square. Fine. That is our final answer. Fractions are typically not allowed though. But yeah, you could write 3 by 8, which is 0.375 CV square. Same thing. My calculator just fell down. Sorry. Yeah. Let's move on to question number 6. 5 was really hard. A heavy aluminum disc has a radius of 0.36. The disc rotates with the wheels of a vehicle and forms part of an electromagnetic braking system on the vehicle. In order to activate the braking system, a uniform magnetic field of flux density 0.17 Tesla and the radius was 0.36 is switched on. This magnetic field is perpendicular to the plane of rotation of the disk as shown. Okay, it's perpendicular. Define magnetic flux. Really important question that we face all the time. What is it? It is the product. It's not magnetic flux density. That's field strength, right? Here is just flux. There are three things: magnetic flux density, magnetic flux, and magnetic flux linkage. Linkage is NBA. You have multiple number of terms. Here you don't. So it's just BA. It is the product of magnetic flux density and area, where the area is perpendicular to the magnetic field. Okay, is the product of magnetic flux density and area, where area is perpendicular to the magnetic field. Calculate the magnetic flux through the disk. Give a unit with your answer. So currently, what is the flux through the disk? It is simply BA. We have the radius. We can find out the area. So let's find that out. The flux, or phi, is equal to B times area, which is pi r square. So B is 0.17 pi and r square is 0.36 square. So 0.17 into pi into 0.36 square, that gives you a value of 0.0692, but we're going to give an answer to 2SF. So that is basically 6.9 into 10 power minus 2. And what is the unit of flux? Remember that flux density is Tesla or Weber per meter square. So what will flux be? If you multiply area with Weber per meter square, you end up with Weber's WB, okay? The disk is rotating at a rate of 25 revolutions per second. Calculate the magnitude of the electromotive force induced between the axle and the rim of the disk. Alright. So EMF induced. We are going to use Faraday's law over here. Faraday's law of electromagnetic induction. So yeah, let's do that. Faraday's law of electromagnetic induction states that the EMF induced is actually equal to the rate of change of magnetic flux linkage. Okay, which is del phi by del t, rate of change of magnetic flux linkage, or you could say that it's the rate of cutting flux. That's what you guys need to ensure. So we know that the change, currently the flux is 0.069 as I've mentioned before. And how fast is that changing? Let's try to figure it out. The frequency is 25 hertz. So we know that time period equals to 1 by frequency. So t is basically equal to 1 by 25 seconds, right? So every second, right? Every second it's moving through 25 times. Every second it's moving 25 times, whole revolutions. And every time the change in flux is this 6.9 into 10 power minus 2. So what will the value of EMF be? This multiplied by 25, you can show the working 1 divided by 25, which is basically equal to 0.069 times 25. Okay, this gives you a value of 1.7 volts. All right, pretty straightforward or standard question, I would say, nothing too hard. The axle and the rim are connected into an external circuit that enables the energy of the rotation of the disc to be stored for future use. The direction of rotation is shown in figure 6.1. Okay, it is rotated like, sorry, it's rotated like this direction, clockwise we could say, if we are viewing from this side. Use Lenz's law of electromagnetic induction to determine whether the current in the disc is from the rim to the axle or from the axle to the rim. Explain your reasoning. Is it from the rim to the axle or from the axle to the rim? Really important. So let's try to figure this out. This is a bit complicated, okay? Is it from rim to axle or axle to rim? Firstly, we need to know that Lenz's law states that the induced EMF will oppose the change that created it. Okay? Lenz's law states that the induced EMF will oppose the change that created it. So what is creating the EMF over here? The rotation of this disc is actually causing some flux to be cut inside this field over here. And we know that the induced current that is produced in the rim is actually perpendicular to the magnetic field. And the force will oppose the rotation of the disc. Like for example, if the rotation is clockwise, then it will induce the current in such a way that a force will be produced which opposes the rotation of the disc. Okay, so let's try to figure this out. Let's look at the answer and then try to understand their reasoning. Okay, let's try to figure this out. Okay, so they've wrote that the current in the disc is perpendicular to the magnetic field, as we know using Fleming's left-hand rule. Or you could say that the current causes force to act on disc. What is the next point? According to Lenz's law, the force opposes the rotation of the disc, and we need to mention that the left hand rule, Fleming's left hand rule, indicates current is from rim to axle. Okay, so let's try to figure this out. Firstly, we know that whenever there's a current in a magnetic field, a force will be felt by it. So initially there was no current, right? But since there's a change in magnetic flux density or magnetic flux on the disk, a current is induced. So that current inside the disk will cause it to feel a force, and it will feel force in such a way that opposes the rotation of the disk due to Lenz's law. And we are going to use the left hand rule to figure out the direction of the current, which they've stated is from rim to axle. See if you guys understand the structure of the answer. Firstly, we have to say that, I'm going to repeat again. We know that according to Faraday's law, since there's a change in flux linkage and EMF is induced, whenever there's an EMF, a current will be generated. And since there is a current present in a magnetic field, it will generate a force on the disk, and according to Lenz's law, it must be in such a way that opposes the rotation of the disk. So these 2 points are clear, right? The induced EMF induces a current, and whenever there's a current inside the field, it must feel a force. The current causes a force to act on the disk, and the force is such that it opposes the rotation of the magnet. These are the rotation of the disk. These are the first 2 points. And also one other thing, the current in the disk is actually perpendicular to the magnetic field, according to Fleming's left hand rule. Okay, so I'm using my left hand now. We know that it's father, mother, child, FMC. The thumb is the force, and your index finger is the direction of the magnetic field, and current is the middle finger. So my index finger, the direction of the magnetic field is pointing from left to right. It's from the left to right. So when do we use right hand rule, by the way? These are 2 different concepts, okay? The left hand rule and right hand rule. So typically we use left hand rule whenever there is a current flowing through a magnetic field. That is when we use the left hand rule. So in our syllabus, the right hand rule is not there, okay? We don't use the right hand rule in our syllabus. That's what you need to know. We always use left hand rule. So at first we need to figure out the direction of the induced current and then input it in our question at hand. So one thing is fixed. The index finger is going to be pointing to the right hand side. From left to right, it's pointing towards the right. And now we need to figure something out. Use Lenz's law of electromagnetic induction to determine whether the current in the disk is from rim to axle or from axle to rim. Is it from rim to axle? I think they're talking, rim is the end, right? I think that's what they're talking about. The rim is the end part over here. So they've asked us whether the direction is from rim to axle or from axle to rim. That is what they've asked. Okay, so let's try to do this. The direction of the magnetic field is fixed. Firstly, index finger is going to be on that side. And hear me out. How would you rotate the disk like this? What type of force would you have to apply? Basically, I would need to use my hand and rotate it in this way, right? So the direction of the force is kind of like this. If you give the force like this, then the disk could rotate like this along the axle, clockwise. But according to Lenz's law, the induced current will be induced in such a way that it opposes the rotation of the disk. So in which direction will the force be felt? Like this. Due to opposing the motion, the direction of the force will be like this, or anti-clockwise, it will cause anti-clockwise rotation like this. So I found out the direction of my thumb. Also, I know the direction of my index finger, which is to the right. So my index finger will be pointing to the right, and my thumb will be pointing out of the screen in a slanted way. Okay, you can also think of it like this. It's coming out of the screen, essentially coming out of the screen. Okay, I'm just pointing an arrow like this. So your index finger should point to the right like this, and my thumb is coming out of my laptop screen right now. Okay, so if you're doing it on a physical copy, it will be coming out of the page. It will be coming out of the page. And where is my, I'm doing it on the screen. Okay, so my index finger is pointing to the right of the screen, my index then my thumb is coming out of the screen, and my middle finger is pointing downwards. So if you do it on the screen, it kind of looks like this. Your index finger is pointing like this, and then there your middle finger, my middle finger is pointing on this side, index finger, and my thumb, okay, I'm trying to draw a good figure over here, and my thumb over here is like coming out of the screen like this. This is the thumb. Okay, this is the middle finger. Okay, so the middle finger actually represents, you guys know, the direction of the current, and the index finger represents the direction of the magnetic field lines, and thumb is the force. Okay, so this is B, and the current is actually pointing downwards like this, so which is from rim to axle. That is the answer behind this. So pretty complicated, but like Cambridge really asks vague questions. It's actually hard to figure out what they want. You may know the answer, but you may not know how to write it down. Okay, so yeah, hopefully you got it. I don't think you need another review. Let's move on to the next question then. Question number 7. 4 diodes are used in a bridge rectifier. This is full wave rectification to produce rectification of a sinusoidal AC input voltage, V in. Figure 7.1 shows part of the circuit, but 3 of the diodes are missing. Alright, let's do this. State the name of the type of rectification. Alright, so this is called full, one sec, this is full wave rectification. Fine. Next, complete the figure by drawing the 3 missing diodes. If only 1 diode is used, it is half wave rectification, and if 4 diodes are used, it's called a bridge rectifier or full wave rectification. Okay. Complete this figure by drawing these. Alright. So, okay, so let's try to do this. Here what you guys need to know is usually they have a crossed relationship. What does that mean? The ones that are crossed are not side by side, basically. Like in a typical bridge rectifier, if it was something like this, it's kind of like this, the typical bridge rectifier that you guys have seen. Usually these two are conducting in one go, the crossed ones are. So here it's the same thing, but the cross relationship will be for this one and this one over here. So usually the one in the bottom left, the lower left, should be pointing to the left as well, according to this relationship that I've just taught you. It should be pointing to the left. This is the first thing. Now let's try to figure out the relationship for the other ones. They will also point in the same direction, by the way. Suppose this one is positive and this one is negative. Suppose current is coming out from this direction. It can't go to the right, clearly, because the way is blocked. It must go to the left, okay? So what does that mean? This diode over here must point to the left, or else that path will be blocked as well. Okay, so this diode on the top must point to the left. Okay, so this that it's going down, it's going down. Now it can't take this route, it's blocked, right? That's the main part. So it goes to this end, goes to this end. So this is the positive end, this is the negative end. Current will flow back. Now it wants to go back to the circuit. Now yeah, it can take this route. It can take this route and come back again, because, or check this out. Why is the upper route wrong? I'll tell you why. Come on, check this. Basically, we've already we exit from the positive junction at the beginning, so we must come back to the negative junction. That is why current will not take this route, rather it will take the route on this side. As a result, if you find out the final diode, it should be pointing towards this side. There you go. And yeah, it will come back over here. So this is one case. And now let's do it for the other one where this terminal is positive and this is negative. So let's try again. I'm going to erase the blue arrows. Current will come out from here. It can't go there. It will go to the left. Wait, I need to draw this again. So it will go to the left, it will go to the left. It can't go up, that route is blocked. It has to go down, it has to go down. See, this end is still positive, this is negative. That's the purpose of a full wave rectifier. The ends of the output will always remain the same. Then it will go to the right, it will go up, and then, hear me out, it came out from the positive terminal. So it won't take this route, it has to take this route up, and it will go back to the negative terminal again. See? That is the logic behind this. So yeah, the crossed ones will always communicate. Like when this is conducting, this will also conduct. When this is conducting, this will conduct. And see that they have the same directions. Coincidentally, all of their directions matched for this particular circuit. Alright. Now on figure 7.1, draw an arrow to indicate the direction of the current in resistor R. Okay. So we just need to draw one arrow. And according to my drawing, you can clearly see the direction. Wait up. Here you go. So it is basically to the right. Basically like this. This is the direction. Just one arrow. Draw an arrow. Arrow indicating current direction resistor to the right. Or you could draw it here. That's fine. Anything works. Alright. Now we have to draw 3 diodes. They wrote in the mark scheme lower left showing pointing to the left, and lower right and upper left showing pointing to the left. V in has an amplitude of this. Figure 7.2 shows the variation with time of V in. Amplitude of V naught. Now sketch the variation of V out. Alright, so it will be the same graph. It's just that it will be a modulus since there is no smoothing till now. So let's see. So yeah, the points will be the same, the points where they intersect. It will be at 0.25 over here as well. Then at 1 again, it has the highest amplitude. It intersects the axis at 0.75 again, so that is over here. And then yeah, the same thing continues. 1.25, then 1.75 again, and highest value at 2 again. So the peaks will be reflected now. There was a peak at minus V at minus 0.5 and as well as at 0.5t and 1.5t. So they will be reflected again to the top. Okay. So let's see the peaks. This part will also have a peak here, and at 1.5 there will be a peak here. Okay. So see how I draw it. Let me just copy this honestly from here. Basically, this part of the graph will be the same, this part over here will be the same, and then this part will be the same like this. And yeah, wait, I need to redraw this part. This part will be the same, here you go, and this part will be the same like this, and the others will be a bit different. So why don't we just paste this over here. I'm just gonna try to input that. Let me see if I can. Yeah, there you go. There you go. And now the reflected parts. How do we draw those? Those are essentially, you know, the reflected parts above and below. You have one over here and another one over here. So this is basically the perfect diagram. But yeah, for freehand, you could just draw like this, you know, go down, you hit 0.25, then modulus again, you come back up, you hit 0.75, then the original graph, then modulus again from 1.25 to 1.75, followed by hitting it at 2 again. Okay, So see if you guys get it. This is full wave rectification without smoothing. It is a sine curve, sinusoidal curve with a modulus. It's actually a plus cos graph, right? With a modulus. That's basically it. Now the power dissipated in the resistor is P. Sketch the variation of power between time 0 and 2t. This is really important. The variation for power isn't going to be like this, it won't be a modulus exactly. It's going to be a bit different because power can't really take negative values, right? Power is v squared by r or I square r. So if we had any negative value in the first place, it's going to be squared and it will turn into a positive value. Okay, so if you square this graph, if you square the graph of this cos graph, what does it turn into? All negative values will turn into positive ones, and also the edges won't be that sharp. It will be quite smooth. And hear me out, the power dissipated is P. We don't know the maximum power, but we can consider one of it to be the peak. So for example, what if I consider this to be the peak power? This is my P max. Okay, so what you need to understand is when you draw the graph of, I've done this in previous variants. I think October November 22 had this as well, variant 4.1 or 4.2. I need to solve those variants. Actually, I haven't uploaded them. So yeah, please do like the content, subscribe to the channel. It would help me a lot with the algorithm, because sometimes I need the ad revenue, right? Because sometimes doing it for free is a bit tough. It's not that free. I'm getting a bit of revenue, but your help would be appreciated. Also consider supporting me on Patreon if you want more content. So yeah, basically it will be a graph that has equilibrium position at the midpoint between 0 and Pmax. Remember this point. The equilibrium position of the new graph will be between Pmax and 0. And some other points, the point where V is maximum, at that point you're going to have maximum power as well. So for example, we are going to have maximum power over here, and then again we are going to have maximum power at 0.5, 1, 1.5, 2, 0.5, 1, 1.5, and 2. These are the points where we have maximum power. Similarly, we will have 0 power at 0.25, 0.75, 1.25, 1.75, 0.25, 0.75, 1.25, and 1.75. So now let's draw the graph. Rather than the previous one, basically it won't have sharp corners like this. It won't have a graph like this. Rather, you guys have to think of this orange line as the equilibrium position. Okay, and I'm going to draw a sinusoidal graph or a cos curve essentially. So basically it will intersect this orange line at the midpoints of these two lines. For example, one will be over here, the other will be over here, one over here, the other one will be over here. So let's try to draw that. Come on, check this. Like this, cos graph. And then it will smoothen out. And then again, it will go up. It will go up. And then again, it will touch this part over here. Well, let me draw this again. There you go. So something like this essentially. Okay, so I can just copy that and paste it. Wait up. There you go. Okay. So let's go for it. Same graph over here. Twice, right? Same graph over here. And also same graph over here. This is how you draw it basically. Obviously you guys can't copy paste that. It sucks for you guys. But yeah, this is the gist basically. Like, it won't have sharp corners anymore, right? Because this is actually the graph of cos square. You learned this in Malus law. The peaks will be the same. Also, where you have 0 voltage, you will have 0 volts there. But rather than being a graph like this, it will instead be curved like this. Okay, cutting some corners over there like this. This is the change that you get actually. It's something like this basically. Okay, get it? So hopefully I could clarify. And this graph, I've seen this is becoming more common recently. The first time I've seen this was in 2020 or something, and now it is more common. So sinusoidal curve with troughs sitting on the time axis, right? And peak power at 0.51, 1.52, and 0 halfway in between each peak. Okay, perfect. Suggest with the reason how the root mean square value of V out compares with the RMS value of V in. So hear me out. For a sinusoidal graph, I think you guys know the variation. RMS value, right? So here, RMS value of V in is equal to V naught by root 2. You guys know the gist already. But here, if you think about it, what have they asked actually? So this is the reason how the root mean square value of V out compares to the RMS value of V in. So how did we get RMS? That is an interesting concept that we need to figure out. What is RMS actually? So RMS is root mean square. How was this done? We actually took literally every value of V in, every value of V in, squared them like mean square speed, right? What do? We actually take every value of speed, square them, and then divide by the number of observations. Here we do the same thing. You take every value of V in, square them, and divide by the number of observations, and that's how you get V in mean square V in. And then after you root over that, you get RMS V in. So in the case of V out, you're going to do the same thing, and you're going to square every single value. So if you square a positive or negative value, what will happen? Same magnitude, it will return to the same value, right? Like something, if I square plus 4, I get, 16. If I square minus 4, I still get 16. So just think about it. The value of V out square will be the same. Mean square V out, and then RMS value of V out and RMS value of V in will also be the same. Okay, because since you're squaring each value individually, it doesn't matter whether it's positive or negative, only the magnitude matters. Okay, and for them we have the same power time graph actually. So we have the same, you could say that you have the same power time graph with or without rectification. So same VRMS, that is one way of saying it. Or you could say that the V square, because power is equal to V square by R, right? That's why they're referring to the power graph. V square time graph is same for both V in and V out. So same VRMS. And lastly, another way, power does not depend on sine of V. So same VRMS. Okay, hopefully I could clarify, guys. Let's move on to the next one. Last 3, 8, 9, 10. We have 10 questions, right? I don't think there's question number 11. Thank God. These are smaller comparatively. Let's finish this. Figure 8.1 shows the lowest 4 energy levels of an electron in an isolated atom. Figure 8.2 shows the lines in the emission spectrum of the atom that correspond to the transitions of the electrons from N3 to N1 and N4 to N1. Okay. So one of them is N3 to N1. I'm gonna color code them, okay? N3 to N1, and the other is N4 to N1. N3 to N1 and N4 to N1. So remember this, guys. The longer the line, this has the highest energy. So the longer the line, the higher the frequency and the lower the wavelength. So clearly, as you are going to the right in this, emission spectrum, frequency is increasing to the right. So which one is the red one? Actually, the one with higher energy, N4 to N1. This is the red one. This one over here. Okay, this is the red one. This is N4 to 1. And what about the purple one? The purple one is this. This is the purple one. So that is the one from 3 to 1. Fine. Now the other ones, okay? Let's talk about the other ones. Red clearly has the highest energy, it's the longest one. Then purple, and then we have 2 to 1, that's another one. They are all gonna lie to the left of these lines because all of them have lower energy or lower frequency. Explain with reference to photons why there is a single frequency of electromagnetic radiation that corresponds to each of these transitions. Interesting. So we know that these energy levels are discrete. They are fixed, not continuous, and they will only take these values. So changes can only, a photon is released when an electron actually jumps down to a lower level from a higher one. Since these levels are fixed, and since the levels have fixed values, so the gap between two levels will also have fixed values. And a photon is released in the first place because an electron jumps from one level to the other. So since these values are fixed, and the gap between them is also fixed, so what does that indicate? That the energy of the photon must also be fixed. Okay, that's the logic behind this. So let's write that down. The transition actually emits one photon with energy equal to the difference in energy between two levels. Really important point. Okay, one transition will release one photon, okay, with energy equal to the difference between two energy levels, and the frequency of radiation corresponds to energy of photon. Really important. Okay, you know that E is equal to HF. So this particular frequency that we're seeing actually corresponds to the energy of that photon, which is equal to the gap between those two levels. And it will never be another frequency. That's one single frequency. Okay, E is equal to HF. On figure 8.2, draw a line that corresponds to the transition of the electron from N2 to N1. N2 to N1. Okay, N2 to N1. So this has lower energy and lower frequency. So it must be located to the left because it has low frequency. And we need to label that line A. On the other hand, we have another one that is a transition from N3 to N2. I'm going to use green for this. N3 to N2. Fine. N3 to N2. Now look at the gaps. N3 to N2 is smaller compared to this. So it has even lower frequency. So this is lower than the blue one. And we need to label that as B. So A is lower than the other two. Okay, so the blue one is line A. It is the transition from 2 to 1. And the green one is line B, which is the transition from 3 to 2. Now check this, guys. Look at the gap between purple and red. Which gap is that actually? This small gap over here. That's the difference between the two energy levels of purple and red. Now let's compare, like basically you guys need to understand that both B and A will be to the left of this pair. Both of them will be to the left. And since B has a smaller energy level than A, that's why it should be further to the left compared to A. Now, what is the difference between A and the purple line? Check this. The difference between A and the purple line is something like this. So it's going to be a bit more comparatively. It's going to be a bit more than this small gap that we had over here. So if I compare it, maybe if I rotate it like this, essentially it's a gap like this basically. So yeah, you could take your scale because then it would be easier to draw, then you wouldn't get a wrong answer. It should be somewhere over here. Okay, so in the mark scheme they just mentioned that a line labeled A, this is what you need to label using your scale, that is on the left of this pair, and the gap between the purple one and A should be bigger than the gap between the pair itself. So my orange gap, the one I labeled here, should be greater than the green gap. They just mentioned that. Okay, but to draw it more perfectly, I've measured it. Let's go to the next one. Draw B. So check this. B clearly has less energy than all of them. And let's just compare the lengths of A and B. Let's just compare them. Because it's hard to actually figure out the difference between those two. Let's just compare them. So basically B is like this. Right, you have to compare them from the same level. Look, I could compare A and the other ones because all of them came to the same level actually, but B is not on the same level. That's why I'm gonna use a trick to compare them actually. Check this. I'm just gonna copy it. Wait, that did not go as planned. Wait up. Here you go. Copy and paste. Yeah, so I'm gonna put it in the same level and compare them. So look at the gap between A and B. What is the gap? The gap between A and the purple one was this, and the gap between A and B is this big. This is much bigger. So I can also take this, I can rotate it and bring it down over here so that I can get the most accurate answer. And yeah, so B should be somewhere over here. So let's take a look at the mark scheme, see if my answer matches. So the mark scheme says that B should be to the left of both of the lines, the pair as well, all three, the pair as well as the green one, and this gap, right? The gap between B and A should be greater than the gap between A and the purple one, the nearer one to A basically. They haven't said purple, but I color coded it to make it simpler. But yeah, the gap between A and B should be greater than the gap between A and the nearest one to A from the pair basically, or else you wouldn't get the second mark. If you just gave B like this somewhere here, you would just get 1 mark. Okay, so yeah, getting full marks over here was in fact rather complicated. So yeah, some questions from this paper were actually very hard, very hard. And both of them are to the left because as you go to the right it's increasing frequency, as you go to the left it's low frequency. So that is the logic behind it. If you go to the left, like the lengths of these arrows B and A are actually smaller than the purple and red one. That is why their energy is less, and you know that E is equal to HF. So if frequency is lower, energy is also lower. Yeah, okay. For C, the frequency of radiation represented by line A is Fa. The frequency of radiation represented by line B is Fb. The energy of the ground state n is equal to 1 is E1. So this is E1. Now, determine an expression in terms of Fa, Fb, E1 and the Planck constant for the energy E3 of level 3. E3 of level 3. This is E3. Interesting. So basically, E3 is E1 plus energy of A plus energy of B. Think about it. Energy of A plus energy of B. If you add those two and add that to E1, you're going to get E3. That's the logic behind this. Because E3 is over here. For example, you know that as you go to higher energy levels, it gets closer to 0, right? So for example, if this is minus 1.20 E1, okay, and maybe this is minus 0.60, for example. So we can state that minus 0.60 is equal to minus 1.20 plus energy of A plus energy of B. So what must they be? Something like minus 1.20 plus 0.40 plus 0.20. So if you do find that out, that is minus 0.60. That is the logic behind this. Okay, so let's write that down. We need to mention the formula E is equal to HF, and we need to state that E3 is equal to E1 plus HFA plus energy of B. So in the mark scheme, they just took common HFA plus FB. That's what they wrote essentially. Same thing, okay? As long as you get it. Fine. So we can say that E3 is equal to E1 plus HFA plus FB. Fine. Let's move on to question number 9. Last two questions. We're not going to take that long. What is the mass defect? You need this memorized according to the mark scheme or the syllabus. It is the difference. It is the difference between mass of nucleus and total mass of nucleons when they are isolated or infinitely separated. When infinitely separated at infinity. So what is it essentially? Suppose carbon 12. You have 6 protons, 6 neutrons. You could find the mass of 6 isolated protons and 6 isolated neutrons and find out the mass of the carbon 12 nucleus. You would see that surprisingly the mass of the nucleus is lower than the isolated mass, because you know some mass is lost as a defect and converted to energy to actually strong nuclear force, because the protons are repelling all the time, right? So to keep them in check, we need a attractive force, that is the strong nuclear force. State the name of particle X. Let's try to do this. 2 plus 3 is 5. This is 4. It must be 1 over here. And 1 plus 1 is 2. So it is balanced. So it has a mass of 1 but a charge of 0. What is it? It is in fact a neutron. Show that the energy released when one nucleus of helium-42 is formed in this fusion reaction is 2.8 into 10 power minus 12 joules. Okay. So let's do this. We need to find out the mass defect first and then input it into E is equal to mc square, right? So what's the mass defect? This neutron has no mass defect because it's isolated. So if we compare the mass on the left and right, let's find out the mass defect first. So X has no mass defect, they mentioned that. Let's just try with helium first. 0.030377 minus the mass on the left hand side, 0.002388 minus 0.009105. That is actually equal to 0.030377 minus 0.002388 minus 0.009105. That is actually equal to 0.018884. This is in terms of U, by the way. Mass defect is not kg, it's in terms of U, usually in terms of U. Now, what do we need to find? The energy released. So we know that E is equal to del mc square. Oh, by the way, since the mass, right hand side, right, and left hand side, since mass is greater on the right hand side, that means some energy was converted to mass. So on the right hand side, mass is greater on the right hand side, so the energy is actually greater on the left hand side. That's the logic. Some energy was converted to mass. That's the logic. Okay, so let's do this. It is essentially 0.018884 into 1.66 into 10 to the power minus 27. That's the value of U given in the data sheet. I just have it memorized. 3.00 into 10 power 8 whole square times 1.66 into 10 power minus 27 times 3 into 10 to the power 8 whole square. That gives you a value of 2.82 times 10 to the power minus 12 joules. Yeah, which is shown. 2.8 into 10 power minus 12 joules shown. Good. Very good. Next. The star in B has radius. What? We're dealing with star? Right, where the fusion reaction is occurring, right? The nuclear fusion. I thought it was in a processor. power plant. It's in a particular star. The strand B has radius of 2.3 × 10⁹ and luminosity of this. All the energy released from the formation of helium is radiated away from the star. All the energy that is radiated from the star has been released in the formation of helium. The mass of helium produced per unit time by the fusion process. Okay. So we know that luminosity is basically, how is luminosity defined as? What is luminosity if you think about it? Okay, so it is the total power of radiation emitted by a star, that is L. Now we know that the luminosity here is 1.4 into 10 power 28. So that power, that is the power produced, total power of radiation emitted by the star. So that is the energy produced per unit time. And we know that for every reaction, this is the energy that is released, okay, when one reacts. Now we need to find out the mass that is produced per unit time. So we can actually find out the number produced per unit time because I know the total energy that is released, and I know the energy released in one reaction, which is 2.8 in 10 power minus 12, and I know the energy released per second. Okay, so I know the total energy released per second, that is the power, luminosity, and I also know the energy released in one reaction. So I can find out the number of reactions occurring or the number of helium released, because you know when one reaction occurs, one helium atom is released. So let's do this. So at first we can write the number of reactions occurring or number of atoms per second or per unit time, which is essentially the total power or the total energy released per second divided by the energy released in one reaction, 2.8 into 10 power minus 12. You guys get it, right? Like for example, if I know that the total energy released per second is 1000 and I know that each reaction is releasing 10 joules, okay, this is 10 joules per second and this is 10 joules. So I can get rid of this. So I know that 100 atoms are being released per second. That's the logic basically. So that is 1.4 times 10 to the power 28 by 2.8 into 10 to the power minus 12, which is 5.0 into 10 to the power 39. So that's a lot of reactions per second. Now what's the next one? We have to find out the mass of one helium atom. So mass of one helium atom, helium 42, that is actually equal to 4 times U, 4U, which is 4 into 1.66 into 10 power minus 27. 4 into 1.66 into 10 power minus 27. That is 6.64 into 10 to the power minus 27. What is the final step? Mass per unit time. Let's use this. Mass per unit time. That is equal to, we have the mass of one atom and the number of atoms released per second. So we can just multiply them to get kg per second. This is in kg. So 6.64 times 10 to the power minus 27 times 5.0 times 10 to the power 39 times 5 into 10 to the power 39, which gives us a value of 3.2, two significant figures. Since our data has a minimum of 2, it's 3.3 into 10 to the power 13. 3.3 into 10 to the power 13 kg per second. 3.3 into 10 to the power 13. Fine, that's great. Next, the surface temperature of the star. So we are going to use the Stefan-Boltzmann constant over here. Okay, so to find this out, we're going to use the Stefan-Boltzmann law, right? So the Stefan-Boltzmann law states that L, or the luminosity of the star, is equal to 4 pi times the Stefan-Boltzmann constant sigma times r square times the surface temperature to the power 4, where r is the radius of the star actually. So it's 4 pi sigma r squared t to the power 4. So we know everything. T to the power 4 equals to, if you input the values, luminosity is 1.4 times 10 to the power 28 divided by 4 pi times sigma, We have to take the value of C. I don't have it memorized actually because I haven't used it much. It's 5.67 into 10 power minus 8. Okay. 5.67 into 10 power minus 8. 5.67 into 10 to the power minus 8. And then times r square, which is 2.3 times 10 to the power 9 whole square, times the no, that's it. Yeah. So 1.4 times 10 to the power 28 divided by 4 pi times 5.67 into 10 to the power minus 8 times 2.3 into 10 to the power 9 whole square. Then you will get a value of t to the power 4 equals to 3.71 into 10 power 15. Then quartic root, right? Quartic root of this, quartic root, that gives you a value of t is equal to 7800 Kelvin. Two significant figures. All right, moving on to the last one for the day. Finally, X-rays for use in medical diagnosis are produced in an X-ray tube. In an X-ray tube, charged particles are accelerated towards a metal target by an applied PD. State the name of the charged particles that are accelerated by the applied PD. So we know the drill. You have a filament lamp which is heated. It is the cathode, and it is accelerated towards the anode, and by thermionic emission we know that electrons are actually emitted, high speed electrons. Explain how X-rays are produced at the metal target. So what happens is the electrons are suddenly decelerated. Electrons are decelerated suddenly. They should have mentioned that in the mark scheme, or they wrote are stopped on impact with the target. Fine. They're stopped on impact with the target, and this kinetic energy is lost by the electrons, right? Kinetic energy is lost by electrons. Suddenly the energy has to go somewhere, right? So what is it dissipated as? It is actually emitted as a photon, and the speed is in such a range, the energy is in the frequency range of X-ray photons. Okay, like remember that whenever electrons are stopped suddenly like this, the energy is converted to any photon, and it just happens to be that the photon is in the X-ray range, so the kinetic energy that is lost by the electrons is emitted as X-ray photons, opposite of the photoelectric effect, right? Like if electrons hit a target metal, if photons hit a target metal, electrons are released. If electrons hit a target metal, photons are released. Calculate the minimum wavelength of X-rays produced when the applied PD is 5.80 kilovolts. Okay, so we know that there is an applied potential difference, and it gives rise to a photon, HF. So the electric potential energy is equal to the energy of photon. So if I break it down further, what is the electric potential energy? VQ, or in this case VE, potential difference applied into charge of each electron, VE is equal to energy of photon, which is HF, or in this case, since they want minimum wavelength, it is hc by lambda. So if you do the math, lambda is equal to Planck constant 6.63 into 10 power minus 34 times the speed of light 3.00 into 10 to the power 8 divided by VE. So the applied PD is 5.80 kilovolts, so that is 5800. So 5800 times charge of electron 1.60 into 10 to the power minus 19. So data is given to 3SF, 6.63 into 10 to the power minus 34 times 3 into 10 to the power 8 divided by 5800 times 1.6 into 10 to the power minus 19. Interesting. Lambda is 2.14. I'm going to give my answer to 3SF as my data is given to three significant figures. Carefully notice that, okay? X-rays pass through a medium that has an attenuation coefficient of 1.4 per centimeter. So calculate the percentage of the X-ray energy that is absorbed by a 2.8 centimeter thickness of the medium. Okay, so to do this, we need to use the formula I is equal to I naught e to the power minus mu x, where x is the thickness of the medium and the attenuation coefficient is mu. So I need to find out the percentage absorbed. If you find out I, you're going to find out the, suppose this is the medium that has thickness of 2.8. This is I naught, and the one coming out is I. Incident is I naught, and the one that is transmitted is I. This is really important. So to find out the percentage absorbed, we need to subtract at the end. Okay, so very careful. This is actually the one transmitted. So intensity that is transmitted by the incident one is actually equal to e to the power minus 1.4 times 2.8. I did not bother converting because both are given in centimeters. E to the power minus 1.4 into 2.8, which gives us a value of IT by I naught is equal to 0.0198. Okay, or basically 0.020. So what is the percentage absorbed? That is going to be equal to 1 minus this 0.0198, that is the percentage absorbed, times 100%. This, because this is the fraction that is transmitted, so the fraction that is absorbed is going to be 1 minus answer, which is 0.98 times 100. That gives you a value of 98%. So 98% of the radiation was actually absorbed by the medium. Okay, so we are finally done with the paper. Now I finally get why so many of you were telling me to solve this. Insane paper, really hard, one of the hardest in recent times. Starting from 2022, I have honestly seen that the papers have leveled up. They've become much harder compared to previous years. So yeah, hopefully I could clarify everything. I tried to give the best explanation possible, but if you do have any other queries or if I've made any mistakes, please comment below. And yeah, I'm glad to say that the channel has just hit 10,000 subs. It might be 20k next year when you're watching this, or maybe much more. So yeah, if you've liked the video, please smash the like button, subscribe to the channel, share the videos, helps with the algorithm a lot. Also, quick shout out to my patrons, my highest tier patrons for the month. We have Luna, Sean, and Deva for this month. If you want to be featured at the end screen, please consider supporting me on Patreon. On the highest tier, you get access to one-on-one video meetings for every month. Basically, you get access to all my solved question papers as well as my notes for physics and chemistry, as well as help with text. And you can request for any question paper solving, which will be on the top of my priority list. Also, I'm gonna link the paper for February-March 2023 photo up here, and the paper for May-June 2023 variant 4.1 or variant 4.3 down here, and the playlist for physics P4 over here. And remember to subscribe to the channel. See you guys. Bye bye.